you're on the Tutor Hotline with Melissa Maribel. How can I help you?
Hi Melissa, this is Brittany. Our problem is from TRO 4th edition, chapter 15, number 83. Ammonia can be synthesized according to the reaction. 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia gas. This is at equilibrium. Kp equals 5.3 times 10 to the negative 5th power at 725 kelvins. A 200-liter reaction container initially contains 1.27 kilograms of nitrogen gas and 0.310 kilograms of hydrogen gas at 725 kelvins. Assuming ideal gas behavior, calculate the mass of ammonia in grams present in the reaction mixture at equilibrium. What is the percent yield of the reaction under these conditions?
20.1%. Let's go over that. First thing you want to do, identify what you're given and what you're finding. We're given our balanced equation as well as our Kp value and at a specific given temperature here. So these are all our givens. We have our volume, we have 2 different masses for our reactants and our temperature. Now we're finding 2 separate things. The first part of this question is asking us to calculate the mass of ammonia in grams. So we're going to start off with that. And then we're also going to figure out the percent yield. This question does require multiple steps. Let's just look at all the different steps that we will have to do for this type of question. We're going to start off with calculating the moles of each reactant. Then we'll get to finding the partial pressure of each reactant, build an ice table, and then we're going to write our Kp expression, solve for X, convert the pressure of NH3 to moles, and finally convert those moles to grams. So let's start off with just the first step here with calculating the moles of each reactant. So we're given both of our reactants in kilograms. We want to convert that to moles. So remember how we do this. This is just some stoichiometry. We're going to go from kilograms to grams and then from grams to moles. I'll start off with the first reactant of N2. So here I have just what I'm given initially, and I'm going to convert this to grams. How I'm going to do this, remember this is using the metric system where 1,000 grams of N2 is then equal to 1 kilogram. And then I always align my units so that they can cancel. So in this case, our grams, kilograms, and kilograms would cancel. And then now I'm at the part where I wanted, which is the grams. So I'm right here. Now I have to convert this to moles. Whenever we're going from grams to moles, we want to use the molar mass to do that. So I need the molar mass of N2. Remember, nitrogen's molar mass is 14.1. Multiply that by 2. And that's what we're going to use. That's the 28.02 grams of N2 per every 1 mole. Now I'll cancel those grams out. And then finally, what we're going to do is I'm going to multiply the 1.27 times 1,000, then divide it by the 28.02. And when we do that, that's going to give us this amount of moles for N2. We're literally going to do the same exact process just for our second reactant of H2. I'll start off with just what I'm given. And then once again, I'm going to use the metric system here to convert our kilograms to grams. Kilograms and kilograms cancel out. We're now at grams. To convert this to moles, we will use the molar mass of H2. So then that's 2.02. I'll multiply these 2 values together and then divide them by the molar mass of H2, and we're given our moles. So that was just the first step. Let's move on to the second step of this. The fact that they give us the Kp value, that should be a huge hint to you that we are going to be looking for the pressure. Okay, so remember that Kp, specifically that P is referring to pressure or partial pressure. And then, however, if this were Kc, C would refer to the concentration. So because it's Kp, that's why I decided, okay, you know what, I will have to figure out the partial pressure of the reactants, and that's what we'll do here. Remember, this is going to be using the ideal gas law, which is PV equals nRT. And then I'm going to solve for pressure. So when we solve for pressure, all I have to do is divide over the volume. So if I divide over the volume, this is the formula that I will be plugging everything into. We will find the partial pressure of both reactants for N2 and H2. I will start off with our first reactant. Literally just plug in everything that we have and that we just found. So we found the amount of moles in the first step. And then I'm going to multiply that by our gas constant, followed by the temperature that was provided in the question, divided by the volume that was also provided. When we do all this math, so multiply straight across and then divide by that 200, we would get the partial pressure of N2. We'll do this exact same concept and exact same thing to find the second reactant's partial pressure. So I'll plug everything in. Now I'm going to plug in the amount of moles we found in part 1 for H2, multiply straight across, divide by 200, and we would get this as our partial pressure. So far, steps 1 and 2 are complete. Now to build an ice table. Now, I know to build an ice table because this question specifically is saying equilibrium. So they're not telling us that it's currently at equilibrium, that this overall reaction is. They want the mass of ammonia in the reaction mixture at equilibrium, meaning it is not currently there. That's why I have to build an ice table. So ice refers to I being the initial. In this case, our ice table would be partial pressure because we found all of our partial pressures and we are given the Kp rather than the Kc. If this were the Kc, then our ice table would only be concentrations or molarity. So instead, remember our I stands for initial, in this case, initial pressure. So I would put the initial pressures that we just found. So the partial pressure of N2 and the partial pressure of H2. So that's what I have so far. Now we have no idea what the initial amount is because it doesn't exist for ammonia because it hasn't reached equilibrium yet. In that case, it is 0, okay? So there's nothing that's given or provided in that case. The next thing here is C refers to our change. And this is typically where we have some sort of variable of X, or sometimes it could be 3x depending on what coefficients are in front. Before I start to do that, there is something that we want to focus on. Because this is equilibrium, there are times that you will see, sure, the reactants are typically going to be negative for the change, and the products are typically positive because they're being produced. However, there are cases where it's the opposite, and this is one of those cases, of course. So what I want to identify is what our Q is, okay? So remember that there are two different expressions that we need to remember and know how to differentiate. So K refers to our equilibrium constant, so meaning it has to be at equilibrium. While Q, it's not at equilibrium. That is the main difference that we will see here. Okay, they both are going to be products divided by reactants, but one is at equilibrium, which is K, and the other isn't, which is Q. I have to figure out what the Q value is, and then I'm going to compare it to the Kp value. So what I'm looking at is for Q, I'm specifically looking at Qp because we're only looking at partial pressure. So in this case, remember that our partial pressure will be as follows, where it's going to be our products on top. So I put the products. Any sort of coefficient is now our exponent. So that's where I got that 2 from, because the 2 is the coefficient of NH3. So that now becomes our new exponent. For the denominator, that's going to be the partial pressure of our reactants multiplied. So this is the partial pressure of N2. There is no exponent because there is no coefficient besides 1. That's why there is no exponent here. And then for this one, the reason why we have that exponent of 3 is because there is a 3 coefficient in front of H2 on our reactant side. So this is our QP expression. And then remember that this is just initial values. It's not at equilibrium. So I will literally plug in these initial values into my QP value and solve and see what that would give us. When I plug everything in, so we don't necessarily know the initial value. We're stating that it's 0 because we're not given anything. So I'll put 0 on top. That's our partial pressure of ammonia. And then on the bottom, N2 was the initial pressure that we found. I plugged that in, and then I plugged in also the initial pressure that we found for H2. When we do all this math, really, you just have to focus on the top here. The fact that the top is 0, that means this entirely will be 0. So we're stating that QP is 0. The reason why this is important is because if we compare QP and KP, that can tell us if the forward or the reverse reaction is favored. So in this case, our reverse reaction is favored, meaning our reactants are favored. That means that our change is opposite. So instead of this change being negative, where reactants are typically negative here for our change, we will have a positive. Okay, so we are actually adding. And then instead of our change being typically positive for the products, it's actually going to be the opposite. It's going to be negative for subtracting in this case. This is specifically because our KP is less than our QP. Okay, and that's always the case for something like this. However, if KP were larger, greater than, QP, then it would be favoring the product side, which is the typical reaction. So then this would have been negative here on our reactants and positive for our products. But that's not the case in this case. So continuing on, the E portion of our ICE table is the at equilibrium portion. So what we would do is we would then combine both the initial and the change. So we are simply adding in this case. We're just adding them straight on down. So I'll add these two straight on down, and same goes for this portion. So this would have been a negative 2x. Now what we'll do is plug everything in. We need to find the KP expression, and it's really the same exact thing as QP. So the expression is, not the value. So in this case, I have the same expression. This is KP. I will plug everything in. So I have -2 for this first portion. So I have -2 for this first part. And then next, our partial pressure of N2 is at equilibrium is such. And same with H2. And then of course, don't forget to put your exponents because that is gonna make a difference. And then finally, what I did here was I plugged in our actual value for KP because that was given initially. The whole point of this now is to solve for X. So that's where we're headed with this. So we're solving for X in this case. What we're gonna start off with, since we wanna solve for X, and this is a bit more complicated of a question, because we have something that's cubed and we have another set of x's really. So what I want to do is just multiply the denominator to both sides so that they can cancel. I want to get rid of that fraction and make this as simple as possible. So when I do that, I multiply both sides by the denominator. This side then cancels out, we remove that denominator, and it's going to look like this. So, okay, we don't have any more fractions, so great. But the next thing we want to do is to set this equal to 0. So I will subtract over that 4x squared, and it's gonna look like this. You most likely have not seen anything like this because they don't teach on this. Typically, you will either see something where the x is small, that sort of assumption, or you will see that you have to use the quadratic formula. In this case, neither of those cases apply. This is more of a advanced question, I would state. So, I looked it up. Why? Because it's a very challenging question, and I wanted to see, is there another way to do this since you typically only learn the x is small assumption or using the quadratic formula, and I don't even remember them teaching me this in school. So I knew, I'm like, well, I know I can do this using math, but you shouldn't have to know this portion of it. But anyways, I looked this up using Chegg, and luckily you provided the book, so they do have textbook solutions. So I found the exact book and the exact question, the solution manual to this question. So I was able to look at all the steps and look and see that yes, this is the only way that you can approach this question. What they have there, I'm glad they have all the steps mapped out. What they have is this, where they have everything set equal to 0, but then magically the answer of x shows up and the textbook solutions don't continue to then tell you where that x actually comes from and how to do this. So it's not magic, it's math. In this case, what we're actually doing is graphing this, okay? The reason why I'm graphing this is I'm trying to find the x-intercepts. The x-intercepts are the x values. So in this case, if I were to graph this out and I look at where it crosses the x-axis, I'm searching for the value that of course is smaller. This 71 is way too large. How I know that is just the fact that it's even larger than any of the initial pressures that we started with, okay? Because that's way too much, I know that that's not the answer. So it had to have been this negative 2.7. That's going to be our x value. The likelihood of this being on a test is not likely, okay? Because you need a graphing calculator, which most classes don't allow you to use either way, okay? But this is probably just an extra credit question or some sort of homework assignment. What I'm gonna do now is I'm going to convert the pressure of NH3 to moles. So we found this x value just to be able to figure out the partial pressure of NH3 using our ICE table. So remember that we wanted this at equilibrium, right? That's what this question was asking. We wanted to figure out the grams of ammonia at equilibrium. So we know at equilibrium, that's going to be negative 2x for the partial pressure. I'll plug in what our x value is into this formula, multiply both of these values, and our partial pressure at equilibrium is 5.4 atmospheres. Now I want to convert this down to moles. So let's do that. This is going back to using the ideal gas law. If I were to use the ideal gas law, I am going to solve for n in this case, so I can just divide over the RT to both sides and then plug everything into this formula. So plugging everything in, I'm still going to use the same volume, gas constant, and temperature that was originally given in the question. And now I'm plugging in the pressure, the partial pressure that we found currently. So when we do this, when we multiply the top and divide by the bottom multiplied, we will get this amount of moles. Continuing further, next step is to find the overall grams. We're going to convert these moles of ammonia to grams using the molar mass. So all I have to do is multiply by the molar mass of ammonia, which is 17.04. Multiply those two together, and we'll get this as our mass of ammonia. So this is the mass of ammonia at equilibrium. So perfect, that's done. Next part of this question is figuring out what is the percent yield of the reaction. Definitely know this mass, this is going to come up again. So to figure out the percent yield, this is another step, another main step question. There's 3 specific steps we want to look at. So percent yield goes back to limiting reactants, theoretical yield, actual yield, and all that. The first thing we want to do is just find the limiting reactant. And what I'm going to do this is I'm bringing back the amount of mass that they give us initially with both of our reactants. That's why they provided us with it. So what I have to do is go from kilograms of N2 to then grams of our product, which is NH3. And this is what it's going to look like. This is the overall plan. So I'll start off with going from kilograms to grams of N2. So I'll start off with what we initially were given, and then using the metric system again, I will convert it down to grams. When we do that, our kilograms and kilograms would cancel out, and now we're at grams. Next, we can convert this to moles using the molar mass of N2. This is going to allow us to cancel out the grams and then get to moles. So because we want to change the compound or molecule, we want to change this all together. What we use is the mole to mole ratio. That allows us to go from one molecule or one compound to a completely different compound. So in this case, I'm going to look at my balanced equation. That's why it was given. So building a mole to mole ratio, placing the moles of N2 on the bottom, looking at our balanced equation, there's a 1 here, right? So there's 1 mole of N2 for every 2 moles of NH3 on top. And now we can cancel out the moles of N2 and N2. And we're here at the moles of NH3. Finally, I can then convert this to grams of NH3 by using the molar mass of NH3. So I'll multiply by the molar mass of NH3, then our moles of NH3 cancel out, and we're left with our grams of NH3. So what we want to do to multiply all this together is we're going to start off with just multiplying everything on top. So I'd multiply this value times 1,000 times 2 times the molar mass of ammonia and divide it by 28.02. After we do all that, we get this as our grams of NH3. I'm going to do this all over, specifically for the second reactant of H2. So same setup, all right? I'm converting everything from kilograms of H2 all the way to grams of NH3. I'll start off with what we were initially given, and then we're going to convert this to grams again. So converting this to grams, using the metric system, we want to cancel out these kilograms. So these kilograms cancel out. Now we're at our grams and we're going to the moles of H2. So I will use the molar mass of H2 to cancel out those grams and get to moles of H2. Once again, we want to use the mole to mole ratio, which comes from our balanced equation, and convert this from moles of H2 to moles of NH3. So on the bottom, what I will then place is we have 3 moles of H2 because there's a 3 coefficient in our balanced equation per every 2 moles of NH3. Our moles of H2 then cancel, and we're now at moles of NH3. Next step here is to multiply by the molar mass of NH3, and then our moles will cancel out. We're left at grams, multiply everything on top, and then divide this by both of these multiplied, so 2.02 times 3. And then after we do this, we will get this value, this amount of grams of NH3. So that was just figuring out the mass of each reactant, so how much each reactant would produce in our product, how many grams. What we want to do now is actually identify what is the limiting reactant. Remember that the limiting reactant is going to produce the least amount of product. So in this case, if I'm looking at this, I see, okay, well, N2 produced this amount of ammonia, and then H2 produced this amount of ammonia. Which one produced the least? Well, N2, so that has to be our limiting reactant. Next, I'm going to identify the theoretical yield. And luckily, we already did this. So remember that your theoretical yield always comes from your limiting reactant. Whatever your limiting reactant produces is your theoretical yield. So we found our theoretical yield already because we found our how much our limiting reactant was going to produce when we were looking for it, right? When we were looking for which one is the limiting reactant. So this is our theoretical yield. Last step here is to calculate the percent yield. Remember, for our percent yield, it's our actual yield on top divided by our theoretical yield and times 100 since it is a percentage. So our actual yield came from this very beginning of the question where we were looking for the mass of our ammonia at equilibrium. That's where the actual yield comes from. Our theoretical yield came from finding the limiting reactant and seeing how much product did our limiting reactant produce. So remember what we found previously is that our actual yield was that 310 grams of ammonia divided by the theoretical yield that we just found. And what we're going to do now is just divide and multiply by 100, and that's where we get the 20.1% yield. If you have homework questions that you don't know how to do or you want to double check that the answer is right, then I recommend using Chegg Study. I am a part of their affiliate program, meaning if you do decide to go with Chegg Study, I get a small commission. But I also like to use it for questions like Brittany's because I like to check my work and see, hey, was this the easiest way I could approach this question? There you can literally find other ways to answer the same exact question, which I like to see. So make sure to check that out. That will be in the description box. All the links will be there. And if you want to get your question answered just like Brittany, then submit a question. Seriously, as simple as that. Check the description box. There you can submit a question using the link. And I'll see you next time.